coming up.
Thank you, Professor Huang. Thank you for inviting me to attend this nice workshop. So I changed my talk, the title of my talk a little bit. So I want to introduce the properties of lanthanum nickel oxides 3 to 7 phase at ambient and high pressures. Professor Arando at the beginning, I would like to thank my collaborators. So many of my group members involved in this work. And in theory, we collaborate with Professor Guangming Zhang in Tsinghua University and Daoxin Yao and Kun Cao in my university at YSU. So for this experiment, we also collaborate with Lingyun Tang, Zhongquan Mao, and Jin Guangcheng's group. Also, we did the high pressure X-ray measurement in Beijing Central Radiation Facility. Very recently, so we collaborated with the mining group.
Sorry, could the audience mute? And actually, I'm not a host, but if one of the hosts, if this keeps up, could mute the speaker. Thank you. Sorry to interrupt.
Okay, no problem. So currently, we are collaborating with many collaborators. They use different techniques to measure the sample and get some very important results. Some of my collaborators are also invited to attend this workshop. So I will not introduce all the work. So that's the outline of my talk. I just go to this slides. Professor Arando has given a very nice talk and introduced the sensitivity on this 112 thin films. That's a very important breakthrough made by Professor Howard Huang's group at Stanford. The transition temperature is at around 15 Kelvin. Now I think it's increases to 20 Kelvin. I just want to point out, actually, there are many phases for this nucleate. On the right side of this phase diagram, that's a so-called Ralston-Popper phases. For these phases, there are nickel oxygen 6 octahedral and apical oxygen. So on this side, it's a reduced RP phase. So I just go to this compound. We discovered the sensitivity in this 3 to 7 compound under high pressure. That's the structure of this material. There are bilayer nickel oxygen 6 layers. Here is the phase diagram. There's a structure transition. Actually, at ambient pressure, it's metallic. But when we measure the sample using the diamond amine cell at low temperature, it's weak insulating. When we increase the pressure, there's a structure transition from AM to FMM structure. And the superconductor transition goes to 80 Kelvin. There's a large stringent metal area in this phase diagram as a function of pressure. The transition temperature decreases a little bit as the increasing pressure. So I guess most of you have known these results. So let's go back to the history of the study of this compound, what we have known about the property at ambient pressure before our study. So here's the structure we have known. Actually, in early days, people have measured the structure using this TEM technique, and we can see the bilayer structure. So there's no doubt the bilayer structure. This compound can be synthesized by solid-state reaction method or the soil gel method. But for the powder samples, there is oxygen vacancy. We can flow high-pressure oxygen and anneal at a high temperature, get oxygen-free samples, while the oxygen is more close to 7. if we flow hydrogen or the other gas at high temperature to a NEO, we will get those compounds with more oxygen vacancies. If for oxygen-free compounds, it's a metallic, we can see here. But with more oxygen vacancies, it will become an insulator. For this stability measurement, we can see the stability increases as we increase in temperature. That means there are weak antiferromagnetic correlations. For the Hall measurement, there's a jump at a low temperature around 100 Kelvin that indicates some change for the Fermi surface or indicates charge density wave. Okay, so the previous studies were on based powder on powder samples. We grow single crystals using the high pressure fluid zone furnace. That's a single crystal, but it's not a large single crystal with the same orientation. But if we correct the samples, the single crystals are in a millimeter size. When we do transport measurements, we see actually there are two transitions, but the anomalies on resistivity are very weak. One at 110 Kelvin. That's similar with the previous one observed on Hall measurements. But the new one at 153 Kelvin, we can see it on these magnetization measurements and the heat capacity measurement. We don't know what's the origin for the two transitions. But later on, Professor Wen's group, they measure the sample with infrared spectroscopy, and they observe a gap opening below 115 Kelvin. Also, the reflectivity show a kink at this temperature. I think they are consistent with this very early Hall measurements. And there's an anomaly at around 100 Kelvin. So that means this anomaly at 110 Kelvin may be related to a charge density wave transition or some changes for the Fermi surface. Okay, so people have interest on the magnetism of this material. Actually, many groups have conducted the neutron diffraction measurements on powder samples for this La3ni2O7 compound, but no long-range magnetic order were observed. However, this Professor Lei Shu's group, they measured this powder sample. Well, if we look at the resistance, it's a weak insulator. That's because the sample was synthesized by a solid-state reaction method. When they measure the sample with mu-SR method, they see very clear oscillation, and they can also estimate the volume fraction of this spin density wave phase. Well, the conclusion for this study was they claim that's clear evidence for spin density wave. The transition temperature is exactly at 150 Kelvin. That's the same with the anomaly at in resistance, and the volume fraction of the spin density wave phase is 100%. So that's very interesting. Recently, we measured a powder sample with the inlet neutron scattering spectroscopy. We also measured the sample with the powder diffraction, neutron powder diffraction, but no long-range magnetic order. When we subtract the data between 7 Kelvin and 300 Kelvin, we see a flat branch at around 45 millielectronvolts. We observe this the excitation with different incident energies. We can see here, here, and here. The incident energies for the spectrum are different. With the very limited signal, actually, we couldn't determine the magnetic structure, but we tried many different structures and simulate the spin excitation spectrum with different magnetic exchange couplings. So the conclusion is the interlayer magnetic exchange couplings are much stronger than the intralayer couplings. Here is a set of parameters we used for this simulation. We can see here the interlayer couplings are 36 millielectron volts, but the intra-layer couplings are around several millielectron volts. There's a range for the parameter, the interlayer coupling and the intralayer coupling, which can reproduce the experimental results, but the conclusions are the same. Professor Donglai Feng's group, they use the RIX method to study the spin excitation on a single crystal. With single crystal, they get this very nice dispersions of spin excitation with Q resolution. We can see here. So the conclusion for this work is there is also a spin density wave along a kind of Lagrange order at the wave vector for at a quarter position. Or they simulated the RIX spectrum with different magnetic orders. The conclusions are the same with our inelastic neutron scattering measurements. The interlayer couplings are very large. It's around more than 60 millielectron volts, but the intralayer couplings are very weak. So because use the RIX method, they can observe the magnetic excitations extends to around 80 millielectron volts. So the exchange couplings are larger than our results. So what's interesting is if they focus on the width and the area of the signal, they see a transition at 150 Kelvin. So that means the transition at 150 Kelvin is related to spins. So there may be a spin density wave order at this temperature. Okay, so I show you the studies based on the diffraction method, but what's the structure if we measure them with this TEM method? Our collaborators, Professor Zhen Chen, they use this TEM and MED method to study our single crystal, and they see very clear the samples are binary phase. Okay, so but there are also oxygen mixes on the inner apical oxygen side. Okay, so here is the nickel oxygen 6 bilayer structure, and this the apical. This is the outer apical oxygen, and this one is the nickel oxygen plane oxygen, and this one is the inner apical oxygen. So use this new they call the multi-slice electron spectrography method. They can observe the oxygen. Okay, so after analysis, they focus on different areas of the sample, and the analysis of the oxygen content for the outer apical oxygen on different areas. They are almost fully occupied, both for the outer apical oxygen and the nickel oxygen plane. Okay, but for the inner apical oxygen, okay, for the inner apical oxygen, for different areas, the results are different. You can see here, some areas is oxygen mixing free, but for some areas, there are more. It's around I think it's 34% oxygen mixes. So That means the oxygen mixes are very inhomogeneous in different regions, but there are oxygen-free regions. More oxygen mixes are located on the inner apical oxygen site. So let's move to the property under high pressure. So this one, we observe superconductivity under high pressure, but here the resistance didn't go to zero, okay? But by combining the resistance measurement and the susceptibility measurement, we know there's a superconducting transition at around 80 Kelvin. So here, we also estimated the volume fraction of superconductivity based on these measurements. It's around 20%. Recently, we also repeated these measurements, and the volume fraction on different samples varies from 8% to 20%. And for the structure and the high pressure, there's a structure transition from AM to FMM. They are all orthorhombic structure. So the different for the two structures are the angle between nickel, oxygen nickel, and high pressure is 180 degree. Recently, our collaborator, Professor Hao Liu, they measured the sample at low temperature, okay, at 40 Kelvin. That's in the superconducting state. The conclusion for this study, okay, was there's another structure transition to I4 MMM. That means in the superconducting state, that's the tetronic structure. So that means A is equal to B. But the band structure, the electronic band structure are very similar for this FMM and this I4 MMM structures. Okay, later on, many groups repeated the measurement and observed zero resistance on our sample. So here is a very nice data, and I will not go to details. Recently, we also observed a transition temperature at 84.7 Kelvin on a single crystal. Professor Li Lingsun's group, they did the modulated magnetic AC stability measurement on the sample. They observed very clear diamagnetic response. That means it must be superconductivity. But the transition is at around 64 Kelvin. They also estimated the volume fraction based on the height of this signal. It's only around 1%, but if we integrate the area, it's around 6%. The reason for the low volume fraction of superconductivity may be due to the inhomogeneity of the oxygen content, as I showed you of the TM data. All the data I showed you were based on the single crystals, but actually use this soil gel method, we can grow powder samples. And Professor Jin Guangcheng's group, they measured those powder samples, use this cubic amine cell with La3Ni oil as the pressure transmitting medium. They can also observe superconducting transition and zero resistance. So we know the superconductivity is very sensitive to pressure homogeneity. If we use the diamond amine cell to measure those samples, we couldn't observe zero resistance. They also doped this compound, the isovalent doping, on the lanthanum site. The transition temperature didn't change too much. So we also know, we know now the isovalent doping on the lanthanum site almost does not change superconductivity. There's a new progress on the study of the superconductivity on this FoUS compound. Okay, that's a tri-layer system. actually several groups have measured this sample, but recently Professor Jun Zhao's group they got a very nice data. They observe zero resistance, the linear resistance in the normal state. They also measure the diamagnetic response. The transition temperature is at around, I think, a little higher than 20 Kelvin. They estimate the volume fraction of superconductivity is almost 100%. Okay, so it's there's no doubt it's a box superconductivity. Here is a phase diagram. There is also a structure transition for this 3-4-3-10 system. Okay, the transition the transition pressure is around I think 12 gigapascals from the monoclinic structure to this tetragonal structure I4MMM. Okay, so the angle between nickel oxygen nickel also changed to 180 degree and the pressure in the superconducting state. So I think the reason for the difference of volume fraction for the two systems may be due to that actually the 4-3-10 system is more easier to be grown because there are a larger oxygen window for this compound. But for this 3-7 compound is more difficult. The oxygen pressure window is narrower. It's not very stable. But once we get this sample, it's stable at the atmosphere environment. Very recently, several groups reported some other stacking structures for these 3-7 compounds. One is the 1-3-1-3 compound. We can look at here. This is there's a single nickel oxygen layer, and this is the tri-layer. There's a long order for this kind of stacking. But the problem is we couldn't separate this phase with the bilayer phase, and also sometimes there are also 1-4 phase and 4-3-10 phase mixed together. But currently, when we measure the resistance and the other properties, actually we are measuring a mixture of different phases. What's interesting is recently Professor Hapkin's group they measured the sample. The majority of this phase is also this 1-3-1-3 phase. The transition temperature is also at 80 Kelvin. Actually, that's very interesting and amazing. Well, if the superconductivity is related to this 1-3-1-3 compound, it's difficult to believe this structure, this phase will have the same transition temperature with the bilayer phase. So I think many questions are still open for this system. Okay, here is a summary of my talk. We discovered high DC superconductivity at 80 Kelvin in the RP phase of nucleus and high pressure. And there's a structure transition. We also demonstrated the superconductivity near 80 Kelvin in our single crystal samples correspond to the bilayer phase. And the oxygen mixes are very serious in these materials, especially for the inner apical oxygen site. The superconductivity is sensitive to the oxygen content. If we want to observe superconductivity, it also requires very homogeneous hydrostatic pressure. That's very important to study the superconductivity and high pressure. We observe magnetic excitation at 45 milli-electron volts, and based on the observation, we can conclude the interlayer couplings is much stronger than the intralayer coupling. Okay, so that's all the information of my talk. Thank you very much.
Thank you very much. Wonderful talk. Let me see, Peng Cheng.
Yeah, so Meng, yeah, very nice talk. I really enjoyed it. Yeah. So I was just curious. I mean, so for the inelastic measurement that you showed, typically you see it's a flat mode of 45 millivolt. So how do you know it's not the crystal field level? I mean, why is it so flat? Why is the level of a nickel? I mean, it's also seemed to be inconsistent with Rick's data, right?
Well, I don't think so. I think it's because the intensity of the inelastic signal is very weak. We can see here if we compare with the Rick's data. Okay, it's actually we are measuring this part. Okay, it's similar, right? Based on the simulation here. I think maybe I should. If we look at the simulation, the low energy spin citation is very weak for this system. You can see here.
Well, why? I mean, why couldn't it be simply to sort of localize crystal field level?
Well, I think based on the neutron scattering measurements, we couldn't rule out this possibility. But if we compare, combine the inelastic neutron scattering measurements and the Rick's measurements, I think we can conclude this signal is from spin excitation. Actually, I didn't show the measurements at low energy. We did the measurement at Pelican. We can see clearly excitation at this several milli-electron volts. Yeah, I didn't show the data here.
That's more convincing. Okay, thank you.
Bye.
Yep. Hi, Professor Wang. Very nice talk. I'm just curious whether you see any clear correlations between the density of the oxygen vacancies and the superconducting volume fraction.
Currently, we didn't see the correlations between them. Well, I think the oxygen vacancy that definitely will change the charge density value and the spin density value. But I didn't show the phase diagram here. Actually, our collaborator, Professor Huiqiu Yuan, they measured the evolution of charge density value as a function of pressure. The charge density value will be surprised, I think, at several gigapascal. It's separate with the superconducting region. So in my opinion, maybe this competing orders is not related with the superconductivity, but even at high pressure in the super state, there may be also spin fluctuations. So the spin fluctuations may also play some role in superconductivity. So for oxygen, currently we couldn't know exactly how much of the oxygen vacancy.
I see. Okay. Thank you so much.
Qimiao?
Yeah, just be very quick. Nice talk, man. So I was wondering, in the previous, historical data on just bulk accessibility, it was very interesting, but looked complicated. And I was wondering whether for these new materials, new generation of materials, whether you've gone back to look at the bulk accessibility.
You mean this 4310 system?
No, 327, but the current materials you have.
You had showed in the introduction like sol gel from the old days.
Okay.
I think that's what he's referring to.
Yeah.
People use this sol gel method to grow thin crystals. Using this method, we can get powder samples with less oxygen vacancies. And actually, Professor Jing Guangcheng's group, they observed superconductivity on those samples.
Yeah, but I'm just wondering whether the the bulk susceptibility versus temperature still looks like, you know, what these old data look like.
If we measure the sample at ambient pressure, it's very similar. If you look at this one, but at high pressure, we don't know. Jin Wancheng's group can, you know, they can only measure the sample below 15 gigapascal. But in this region, okay, in this region, they couldn't observe simulativity from susceptibility measurement.
Okay, yeah, you just said that this susceptibility doesn't look to me like just a simple spin density wave. No, there could be disorder and other things that that's affecting it. So thank you very much.
Thank you.
Okay, I think we'll have to move on. Thank you again.